So today it's a pleasure to have Professor Ya-Hui have a colloquium today. Professor Yang was graduated from NCU and then was a postdoc at NCU for a year and then visiting Berkeley for the lab for another year and then came back to Cheung Kong University for a researcher position and then moved back to NCU as a professor. Professor Yang is an expert on solar physics. Today we should be talking specifically about hard X-ray radio signatures from solar flares. Let's welcome Professor.
Thanks for the introduction, and I will say thanks Dr. Chen Ken for inviting me to come here and to give you the talk about my research in solar physics. And you can interrupt me during the talk if you have any questions, and I will try my best to answer your question. Even my English maybe not so smooth. Okay. Before start to the research part, I would like to talk something about the characteristic of solar flares. When we see a flare, when a flare occurs, it is common to see a brightening, sudden brightening on the sun, especially in the UV image. And this brightening indicates the sudden release of magnetic energy in a very short time, maybe within few minutes. And this released magnetic energy then converted into the particles kinetic energy and the thermal energy, resulting in the plasma heating and also particle acceleration. And also during the flare, we can detect various of radiation from the radio through the optical, even to the X-ray and the gamma ray. So when we talk about solar flares, we are actually talking about the energy storage and the release, and also the particle acceleration. Here shows some flare simulations seen in different wavelength images. So you can see there are some brightening in UV. Here, there's a flare occur here. And this something like a spike structure is a saturation effect. It's detected by the detector. And sometimes you can see the ribbon structure in H alpha, and also in UV image, this ribbon structure. And if you see the high X-ray, it is common to see the kernel structures in high X-ray image. And if we use the shock X-ray, the shock X-ray usually can observe something like the thermal loop structure. And you can see the loop structure connect to conjugate footpoints or the ribbons. Okay. And I just say that during the flare we can detect a various of radiation. So, but please note that the response of different radiation are different. For example, in the early stage of energy release, we call the impulsive phase. The strong and the sudden response come from the X-ray and the radio. So that's why we want to use the X-ray and the radio observation to detect or to investigate the energy release or particle acceleration in the early stage of flare. And theoretically, the magnetic reconnection is usually responsible for the occurrence of flare. And the first image, like this is the solar surface, and there are a series of magnetic loop. Okay, and if the orange one and the yellow one, these two anti-parallel magnetic field move together and together, move closer and closer, then something happens. Something means magnetic reconnection happen. So it's magic, very magic. So when magnetic reconnection happens, you can see something like the arcade field just below the reconnection side. So what I mean is you can see this field line and this field line, this two anti-pair field line move together, move closer. So this line will, this green line, this original line will broken and then connected to the yellow line. So you can see the below field line like this one, and the upper one become like this one.
What's the scale?
What's the scale? You mean a whole scale?
Yeah, whatever scale.
The scale, it's interesting. The magnetic reconnection can occur very localized. Yeah, and I don't want to go too detail about the reconnection. I just tell students it's like the reconnection site is like a black box. So I mean, there are a strong current and maybe a strong resistivity inside the reconnection line, and we call the diffusion region. Yeah, so I just talk about after and before and after the reconnection. Yeah, so after the reconnection, and the reconnection should occur at this height. So after reconnection occurs, you can see below the reconnection side there are lots of arcade field, and above the reconnection side there is something like a HEX magnetic field structure. Okay, and so I will say the reconnection is a metric in star phase or in space phase, because through the reconnection the magnetic topology change, and also after reconnection the magnetic energy will be released, and then plasma will get hit, and the particle will get accelerated. Okay. So by combining with the observation and the magnetic reconnection theory, the so-called standard software model is developed. So as mentioned before, there is a silver X-ray observation, something like the silver loop, and this loop connects with two footpoints, and this two footpoints is observed by HXR, and this HXR source we call the HXR footpoint, and this two source is just located at the chromosphere. But there is another HXR source to locate the upper, like this one. So we call this HXR source just above the root type. And this HXR source, you can say this HXR source is called a corona HXR source. And these HXR source are caused by energetic electrons, which is accelerated during the flare. So based on this observation, we suggest that there is an acceleration region, or we call the energy release region, okay, above the HXR source. So combined with the reconnection theory, reconnection should occur here, and then accelerate the particle. And this energetic particle will move down to the lower atmosphere. So first collide with the plasma here to produce the corona HXR source. And some other particles keep moving to the lower and lower to the dense chromosphere, and to produce the other kind of HXR source, that is two. Okay, and this heated plasma will move outward due to the thermal conduction, and to occupy all these bare loop. So this variable can be observed by soft X-ray. Okay, so this one is we call the standard standard solar flare model.
Sorry.
Yeah.
Where is the helix, the magnetic field?
Oh, good. Here. Here, this one is something like the arcade field, right? So, like this one, right? Because reconnection is supposed to occur here. So, below the reconnection side, there will be a arcade field formed. So, this arcade field, just like this one. And how about the upper part? The helix field. The helix field will become a part of coronal mass situation. Okay, so like this one. Because this is just a cut plane. So that's the helix. That's a helix field. It's just something like 2D. So we can see 2D. Okay, something like 2D. Yeah, here is a snapshot. So we just talked about the connection occur here, and the accelerated particle go downward, and to produce to form the thermal flare loop like this one. So this thermal flare loop just form just after the reconnection occurred. So the solar X-ray loop just like it forms a cluster shape. When this heat plasma cool down, then you can see another loop structure showing in the EUV. Okay, and at the same time, maybe you can also see the ribbon structure. The ribbon structure appear in the H alpha or UV image. Okay, so that's for one time. But when time goes by, then the reconnection should occur at outward magnetic field. So it is supposed that the cusp, the shape of cusp, or the height of cusp should getting higher and higher. And these two ribbons should be moved hour and hour. Okay, so something like this one. It is a local observation. So this is the X-ray observation. So that's the cluster shape, like this one. That is, we will say this is the a flare loop just reconnected. Okay, so the plasma still hot. So it can be observed by solar X-ray. Okay. So as time goes by, you can see the cluster shape getting growth. So the height getting higher and higher. And then when you see the H alpha or something like the UV image, there are three wavelengths observation combined together. So you suppose see a ribbon expansion like this to record. So here, and here. And I don't know, I'm not sure if you can see something like the loop structure seen in a UV. And this loop, just like the hot plasma cool down, and form the something like the arcade loop, and it can be seen in the UV. Okay. So that's the observational evidence for reconnection. So I will say the software is a result of successive reconnection. Okay.
So why there's no radiation on the upper loop in helix?
Wow, yes, there will be. Yeah, there will be,
Okay.
yes.
So in terms of time scale, that's in a few minutes. event?
You mean this one or this one?
That one. Or either. So
Oh,
time
no.
scale is different or similar?
That's
That's a few,
half an hour or more than
Hour.
half an hour. Yeah,
it takes so long time.
yeah, because it's soft X-ray. When you see the partial, okay, sorry. If you see the line curve of soft X-ray, it should be a gradual variation. The soft X-ray, right, this one.
So that's a minute.
The minute you can see something like, I see. But that depends. Because one kind thread is just maybe start to end just a few minutes or within 3 minutes. But the one larger one or greater one, it can be last near to 1 hour. So that depends. The event. Okay. So far, we have some basic information about the field. Then we can move to the research part. Okay? So, previously we just talked about the bottom. Yes. We also will talk about the upper one. So, that's right. There are another upward energetic particle. And this upward energetic particle can cause the radio burst. Okay, so today I will talk about 3 parts. One part is about the acceleration side, or you see the recognition side here. I will talk about the particle acceleration, just focus on the electric field acceleration at this one. And the bottom one, I just focus on the HXR Footpoint. But the HXR Footpoint emission, you can see there are different emission at a conjugated footpoint. Okay, and then the third one, we will go to the upper one. Okay, when recognition occurs here, yes, there will be upward and the downward energetic particle.
Just
Wow.
upward.
Upward. Yeah. That's keyword. Upward.
Sound control, huh?
Voice recognition.
Gentle in real
I don't touch anything, right? Voice control.
What's going on?
Upward.
Nobody touches anything. Where is it? This one.
This happened before?
Never.
Never. Yeah, magic.
Magic.
Yeah, magic.
Okay, I have a question.
Yeah.
So going back to one slide, your slide before, when you showed the different wavelengths of flares. So do you always see flares in different wavelengths, such as this one? You have soft X-ray, you have EUV, or how does that happen? Do you always have you can see the wavelength changes with time or not?
Okay, because it usually, yes, if we have the multiple wavelengths observation, we can see many of these features, but it occurs at different flare phase. I would say sometimes before a flare, we can see something like the S shape or inverse S shape on the soft X-ray image. And this shape indicates the complex magnetic field structure. So when you see such kind of structure, you can assume that there will be a flare or explosion over there. Yeah. And when a flare occurs, we can see some brightening in UV. And in a gradual phase, we can see the ribbon structure in HR or UV or post, something like this. The post, we call the post flare loop structure. It just happen in the later phase of flare.
So when you image in time, if continuously, then you'll be able to capture the at different location through one flare event.
Yes. Yes. Okay. So I can say I'm all right. Okay, for our moving part, I will talk about radio burst. Okay, so first let me go to the particle acceleration. Okay, here shows one event, very large, extreme flare, very large flare, and you can see the background image showing the loop structure, and also overlaid by the ribbon structure, and also you can see the HXR Footpoints over there. Yeah, but it is clear that there are two sets of loops. One is here, set 1, and then the other is here, set 2. What are the difference? You can see if you combine or compare the loop structure, you can see for the set 1, there is no any hard source over here, and the loop structure just like a weakly shear. But for set 2, you can see I think the loop structure is highly sheared, not just like an arcade or dipole, and also over there with the HXR Footpoint.
So how you could tell whether that's the lower part or upper part?
You mean?
Well, yeah, well, whatever loop or arcade shape, how you can tell whether it's upper side or lower side?
This one, because you can, I think, because this image is taken at 195 astron. So then that should be in the lower corner or transition region. So I think that should be the lower part.
Because of energy?
Because I think because of the reference we use.
I see.
And later we can see something like the radio source or high source in the upper part. Yeah, we do have some that.
So you can tell the difference based on the frequency or energy.
Sometimes it's hard.
I see.
It's hard because I just say in principle there should be two kinds of hardware source, right? One is we call the hardware Footpoint, and then the other one we call the above the rooftop source, the hardware source. But it is usual that this one, the upper one, is weaker than the other one. So sometimes we can detect the hardware Footpoint, but cannot see the upper one. Yeah.
So there's such a model or?
Because we did observe both. And yeah, because usually if the flare just occur near the limb side, it should be easier to catch up these two kinds of source, right? Yeah, but if the flare just occur on the disk side, it's hard to distinguish this source just located the loop or at the top. But we can guess from the energy. Yeah. Okay. So our purpose is to calculate the electric field. At least two kinds of loop structure, and to compare with the HXR approximations. How do we calculate the electric field? Just very simple. Now we're starting from the particles, and by assuming that the magnetic flux along the magnetic field from the photosphere to the corona is conserved. And we also assume that the ribbon length is longer than the width. So our idea is to use the photosphere or chromosphere measurement to derive the electric field in a corona, because we don't have any observation. I mean the real data from the corona. We just have the image. Okay, so we use this formula to calculate the electric field and got the following result. Okay, the first panel is the electric field variation for the set 2. That's a highly shear arcade field. And the second one is the electric field variation at set 1. Okay, and then the third one is a spectral index gamma. Okay, let me explain. The gamma value, the low gamma value means the spectrum is harder, indicating that more particles can be accelerated to higher energy. Okay. And for comparison, we also show the HXR line curve as the green curve. Okay, so you can see 2 features. One, the E2, the electric field at the high shear region is higher than the electric field at the low shear region. Okay, and the second, known as the vertical line. Okay, you can see the E2, the electric field. The E2 just get approached to the peak just before the high X-ray emission becomes stronger, and then the E2 approach to the peak just before the gamma value start to decrease. What does that mean? That means more particles can be accelerated to higher energy at the highly shear arcade field region by a larger electric field, and then produce stronger high X-ray emission at the chromosphere. This is what we got. Okay. And during the analysis, we found that the HXR Footpoint emission usually appear as asymmetry. You can see here. Here are the contour indicates HXR Footpoint. Here there are 4.2, and here are the 4.1, and then you can see the 4.2 is stronger than 4.1. And we want to know, is there any relationship between the HXR Footpoint emission and the photosphere magnetic field? Okay, so we define 2 parameters to calculate the asymmetry. So one is AH. AH means the asymmetry of high X-ray Footpoint. So you can see the AH always positive, because I always use the stronger one. The stronger substrate to the weaker one. Okay, so AH is for the HXR Footpoint asymmetry. And the other parameters is the asymmetry of magnetic field. Okay, so you can see the AB can be positive or negative. The negative AB means the strong HXR Footpoint located at weaker magnetic field region. Okay, so here are our results. You can see most of the HXR Footpoint located at the weaker magnetic field region. So how can we explain it? We think that this result is consistent with the scenario of a symmetric magnetic mirror. So something like this one. Here is the magnetic field topology. But here there are two footpoints here. But the magnetic field convergence are different than this footpoint. So here, this one have a weaker magnetic field, and so you can see the dot cone have a larger the angle. So more particle can go into the dot cone and then precipitate into the lower atmosphere to produce a strong partial emission. So this scenario can be used to explain our results. Okay. But yeah.
So because the magnetic field has a direction,
Yes.
so you the attract ions, the charge is different, right?
Yeah.
One is positive, one is negative. So what's the balance of these two? Or there's a more electron in one side and ion on the other side.
I forgot to mention that this high-strength emission is commonly or quite often produced by the energetic electrons. So almost all our electrons to produce such kind of hardware source.
Yeah, but if the electron, they will concentrate on the other one side because the magnetic field, it will follow the magnetic field.
I see. Yeah.
Yeah, you eject from this side to that side, or from other side. Depends on the magnetic field, right?
Yes. So you mean if electron go to this side, then no electron go to the other side because
Yeah,
of the.
magnetic field direction give you this constraint.
Okay.
Or they are mixed. Magnetic field is mixed. No.
I will say the magnetic field is very complicated, and so you cannot just imagine that the electron just go one way and then cannot go the other way. I would say that, yeah. But your point is right, yeah. Okay, and here shows two events. Because these two events shows the reversal of HXR symmetry. So I'm showing the second panel. That's the AH radiation. So you can see the sign of the AH just changed in the later phase, like here and here. But for the left case, you cannot see any corresponding sign change in AB. But you can see the corresponding variation in HXR light curve. Okay, but on the other hand, for the right case, we also see the edge change sign here, but we cannot see any corresponding variation in HXR light curve. But we do see the AB also change sign at the same time. So I want to say that yes, we do see the AH change sign in a different flare phase, especially in the later phase. But this signature can be examined by the different energy release situation, or just a different magnetic field region. Okay, so but this case is very rare, very rare. Yeah, I think, as I remember, there are just two cases in our 22 study. So the percentage is very low. Yeah. Okay. So now move to the other one. Okay. Here shows the observation by Nancy radial heliograph. So the contour is the different radio emission at different frequency. Okay, so we first focus on this, the bottom side. Okay, the bottom side. Oh, okay. Here just show the observation from the HXR. So the bottom one, yeah, just consistent with the so-called standard software model. You see, there are a rooftop source, HXR source, and there the rooftop source, and there is a soft X-ray loop, thermal loop. Okay, and the other kind of HXR source here. And also, that's for the downward electron beam. Then for the upward electron beam, you can see the corona source here. And when the electron beam just keep moving outward, you can see some radio source at the higher energy, or even into the interplanetary space. And I want to say that you can see that the radio source is quite larger than the HXR source. That's just due to the lower resolution in radio imaging. Okay. Now we can focus on the upper part. So it seems like there is a feature, all kinds of feature. You can see the different contour correspond to the different frequency radiation, radio emission. Okay, so it seems like the radio emission at lower frequency just located higher, right? Why? What's that? Because
You can see those at the same time?
this one? Yeah, almost at the same time.
That's the time, okay.
Yeah, almost at the same time. What's that? Because the radio radiation is emitted by through the plasma emission. So the frequency is depends on the plasma frequency. So depend on the plasma density, the local plasma density. Okay. So reconnection occur here, and then the upward electron beam go far away. Maybe go to the interference space, and the plasma density is higher, and then become lower and lower. So when the upward electron beam have some chance to collect or to emit radio emission by plasma emission mechanism, then we can detect the radio source. And the frequency of radio source just depends on the local plasma density. Okay. So that means we can detect radio source at higher energy, no, at higher frequency. Yeah, high frequency, and then become lower and lower when this electron beam move outward to the interface space. Okay, so the idea is, if we want to detect the information around the reconnection site or energy release site, we must use the radio observation at higher energy. Okay. Now, let me show the result of radio observation. Okay. And here is just one X-ray event. And that's the background image is the dynamic spectrum. And the blue curve indicates the soft X-ray light curve. So I say the impulsive phase or the early stage of energy is curved here. is here. So the white one indicates the strong emission, strong radio emission. So you can see here, there is a strong radio emission over here. And this strong radio emission we call the tapestry radio burst, the tapestry. Okay, and usually the tapestry radio burst is associated with magnetic condition, or say associated with software. And at the later phase, there is a signal, radio signal over here. And this radio emission we call the type 2 radio burst. And this type 2 radio burst is usually related to the CME driven shock or interplanetary shock. And you can also see something fine structure over here and over here. Okay, so let's go into detail about this one. Okay, that's the early stage of flare. So here we just say this one is type 3. But if you go into detail, maybe you can distinguish there are two kinds of drifting ray. One is like this one, and the other is like this one. So what is two different? Okay, we call this one is the normal type 3 radio burst, and then this one is reverse type 3 radio burst. What's normal? What's reverse? The normal means if the energetic electron is produced at the reconnection site, then this electron beam move outward, right? So when it move outward, the local density will become lower and lower. So the radio emission, the frequency of radio emission should become lower and lower. So that's called the normal case. So you can see here, as time goes by, the radio emission from this curve from high energy to the low energy. That's what we call the normal type 3. So this one is produced by outward electron beam. And how about the reverse case? The reverse means when the electron beam or energetic electron is produced at the reconnection site, then this energetic electron moves downward. So this electron experience higher or needs higher and higher density. So the radio emission should emit at higher and higher frequency. That's the reverse type. So you can see as time goes by, the radio emission start from lower energy to the lower frequency to the higher frequency. So we call this is reverse type, and then this is caused by the downward electron beam. Okay, so what's the separate frequency? One is upward, and then the other is downward. So the frequency should be the site of particle acceleration, near the particle acceleration site. Okay, so that's the tapestry. We call that's the tapestry pair radio burst. Okay, and then you can also see some weak group of spike. But the drifting rate, you can get a common drifting rate. I mean, the normal or reverse, you cannot tell. It's very random. Okay, so how can we explain such kind of feature? We suggest that reconnection occur here, just near the site for this frequency. Here. reconnection occur here. Then our electron beam cause the normal tapestry, and the downward electron beam cause the reverse tapestry. And how about this one? How about the spike one? Because the spike one just occur around the tapestry, so it should be related to the flare occurrence or the reconnection. So we suggest that there are outflow plasma, and when this outflow plasma impact to the magnetic loop, then will form a shock, and then this shock will accelerate particle and cause something like a spike radio emission.
Does this always happen in impulsive flare, or they are only associated with CFE? So those, according to time scale, it's only half an hour.
Half an hour?
You know, how long?
I'm sorry, it's
What is that flare? Impulsive flare, or is it?
it should be impulsive flare. You mean in time, right?
Yeah, so I'm just wondering whether this phenomena happening for all impulsive flares, or this is how to distinguish this between two different kind of flares? Is it
That's the meaning. So that's 20, and that's 1 minute, I think.
So this is 1 minute.
Yeah. Yeah. So it's very short. Yes, that's 1 minute. So it's very impulsive. Okay?
So you said spatially you are not really resolving such a structure, right? Because the beam is big.
Yeah. Huh?
So you could really tell there's such a moving with such a big beam just by looking at this spectrum.
Not really. You mean this one or this one?
Well, whatever you said, the up or going out and going down, whatever things.
Actually, when, yes, we can say it's upward, downward. Just seeing the we call the drifting rate or the drift. Because when you the signal start from the high frequency drift to the low frequency, we will say this signal should be produced by the electron beam moving outward. Yeah.
Right, but you are just looking at the one position with a bigger beam.
Yeah. Because we don't have the image. If we do have the image, but we must use another spacecraft, something like the SDO, the UV image to locate the flare occurrence. No, the flare side. Yes, we do, but I just remove such kind of stuff. Yeah.
Okay.
We do watch or observe the something like the radio source and the hardware source in the image, and we do find the flare side. Yeah, but we cannot determine the height. Yeah, that's why we must use the radio or dynamic spectrum to say something about the reconnection side. Okay, now move to the later rays. Okay, here this one is a type 2 radio burst, and then you can see two curves. One is fundamental and one is harmonic. Besides, we can also see something like a spike-like burst, just overlap on the type 2 radio burst. And I just said before that the type 2 radio burst is usually caused by the CME-driven shock. So if the CME move fast enough, then there will be a shock just form in front of the CME motion. But the other paper say this CME is not move so fast. So there will be a shock, or there will be a shock, but the shock strength is not so strong. So maybe there's not, I mean, such kind of spy-like burst may be not caused by the shock, because the CME is not moving so fast. So how do we explain such kind of feature? Yeah, here is a theory, because so reconnection and the hex, the upper part, the hex magnetic field is a part of CME. So the CME will move upward. Okay, and I just said if the CME move fast, there should be a shock in front of the CME. But the CME in this case is not moving so fast, so there will not be a shock over here. So we think that when CME moving, there should be reconnection occur here between the moving CME and the background plasma, background solid. So that causes such kind of spy-like burst seen in the radio spectrum. Okay, that's our scenario.
So you are saying you have a impulsive flare
Yeah.
going out together
Mhm.
with a CME.
Yes.
So you are suggesting them happening together rather than separately.
You mean a flare in the CME?
Either the impulsive flare and the CME, yes.
Yes. I said like this.
Okay.
Yeah. Okay. So, this is from the other data. I mean, ground-based radio data. Because I just say if we want to get more information about the reconnection side or energy release side, we must use radio observation at higher frequency. So we use the radio data in Huairou, China, because they provide the radio spectrum in a range of 2.6 to 3.8 gigahertz. So it's almost near the microwave radiation. Okay, so for this study we focus on the type 3 radio burst, but before flare, because we want to look for if there are any signature for flare occurrence. So we just focus on the pre-flare type 3. So here the yellow one, no, not yellow. Sorry. The gray one indicates the flare period. So here is an anchorage flare. Okay, and we detect 9 pre-flare type 3. Maybe half an hour before the flare. So here shows the spectrum, the radio spectrum for this line pre-flare type 3. Okay, not so strong, but it is still good. And we also look from the solar observation. So we go to see the ASIAA image, and we do find to localize region with brightening, with UV brightening. Okay, because I just say it is common to see type 3 radio burst with magnetic reconnection. So when magnetic reconnection occurs, it should have some plasma heating or particle acceleration. When you have heating, then you might see some brightening in image. That's our idea. So we're just looking for the AI brightening. Yeah. And we find to localize area A and B, showing the brightening in some time. And then this active region, just the active region for the following flare occurs. Okay.
So what's the image? Is this a radio?
You mean
What's the
the
image you are showing here?
oh sorry, that's a UV, the 171 electron. Yeah, so that's a UV. Okay, so because we want to look for the brightening, the relationship between the brightening and the tapestry, preferred tapestry. So we just apply all the different reference light up. So there are 7, 1, 2, 3, 4, 5, 7. Yeah, 7 reference. And the vertical line indicates the onset time of tapestry radio burst. Okay, so the left one is for region A, and the right one is for region B. And in total there are nine preferred tapestry. And you can see for the thickened to the fixed tapestry, it should be a curve or related to the region B, because you can see the temporal correlation between the widening, the light curve enhancement and the occurrence time of tapestry. Okay. And for the first one, and the 7 to 9 should be related to region A. Okay. But for each image there are different response curve. Here shows the AIA image, the AIA response curve for different wavelengths. For example, for the 94 electron emission, it is composed of low temperature, or you say cold temperature, cold plasma, and also the high temperature or hot plasma, right? If we see the brightening in the 94 image, we do not know this brightening is coming from cold plasma or hot plasma, right? Because the response curve shows there are 2 peaks in the cold plasma, in the low temperature and the high temperature. Okay, so we want to know if the brightening in 94 image is coming from the hot plasma or not. So we adopt the formula or the method just presented by Leonard in 2013. Using this formula, we can derive the contribution of hot plasma from the 94 image. Okay, so the upper one is for region A, the bottom one is for region B, and here shown the something like the light curve. So green one is the major light curve from the 94 image, 94 electron image, and the dark one, the red one, is the box or the intensity from the hot plasma, just using this formula. Okay, so from these 2 plots, we can say the brightening in 94 image should be mainly coming from the hot plasma. Okay, because you see it's very close between the green line, the green curve, and the blue curve. The blue curve. And we also check the map, the image from the hot plasma shown here. So that's the region A and the region B. And the dark one indicates the the high density of hot plasma. Okay, so you can see the hot plasma just very dense at region A and region B. So we suggest like the 94 image, the brightening in the 94 image should be mainly come from the hot plasma contribution. And because we see the temporal correspondence and also the spatial correspondence between the brightening and the tapestry occurrence time. So we think and we suggest that this tapestry, the preferred tapestry, should be due to the local plasma heating, because we see the hot plasma, should be due to the local plasma heating produced by the local magnetic condition. Okay, so that's one case. And I will show the other case. Here is another M case. And this case, there are only two preferred tapestry detected. Okay. And we also look for the solar association for such kind of tapestry. And we do find the temporal correspondence between the tapestry and also the brightening. Each curve indicates the light curve from different wavelengths. Okay, and there is also the spatial correspondence between the brightening. So we got the same conclusion. The preferred tapestry should be related to the local heating due to the local magnetic condition. Okay, so let's make some summary. First, sorry, many words. Yeah, first we focus on the reconnection side, and we calculate the electric field, and we got the consistency of the consistent with the standard Fourier model. That means more particles are accelerated by a larger electric field as the high shear magnetic field to produce strong hot source. Okay. And then we move to the footpoints. So we investigate the asymmetry of footpoint Huxley emission, and we found most of the strong Huxley source located at the weaker magnetic field region. Okay. And then finally, we move to the upward electron beam to analyze the radio burst, especially the texture radio burst. And we found that there are lots of fine structures, and we give some explanation for each kind of fine structures. And we also look for some evidence to give some evidence of Fourier occurrence. So we look for some signature of Fourier tapestries to say maybe there is some relationship between the preferred tapestry and the localized magnetic condition, and it should be related to the occurrence of following Fourier. Okay, that's all. Thank you very much.
We're out of time, but good questions for Professor Yang.
When you calculate the electric field,
Yeah.
you have to know the strength of the magnetic field,
Yeah.
right?
Yeah.
So how did you get the magnetic field strength?
Yeah, the magnetic field is just derived from the photosphere. I mean, because we have the photosphere magnetic field, we can. Let me show you. background image is the line of sight magnetic field. The line of sight magnetic, just measure at the photosphere. Okay, so the white one indicates the outward magnetic field, and the black one indicates the downward magnetic field. So we do have the magnetic field strength, but just on the photosphere. So we use the.
So you can quantitatively know the strength of the magnetic field on the surface.
Yeah. Yes.
I'm curious what's the scale of the magnetic field strength on the surface of Earth, solar.
You mean the scale is the strength scale or
Strength,
the
strength,
spatial?
strength.
In activation should be around maybe few hundred Gauss.
Few hundred Gauss.
Yeah, few hundred Gauss, or even stronger for activation.
Yes, sure.
One last question.
So you always see the paired F3 layer?
You mean OS?
Yeah,
I would say
because
it's common to see lots of tapestry, but not every tapestry can correspond to flare. Because when you just observe the jet, because the jet is also supposed to be produced by the reconnection. So even we cannot see the flare, even we just see the jet, then we can detect the tapestry, because the tapestry should be related to the magnetic reconnection, not just for the reconnection, not just for flare.
Right. If you got more questions, you can find Professor Young in the visitor's office. You're gonna be staying for the day?
Maybe.
Maybe, maybe not.
Maybe.
I guess you'll always be reached by email to support. So if you have more questions, do whatever ways possibly think of to reach her. On that note, let's thank Professor Young again.
Thank you.